It's been a while since I did any videos for YouTube, and as some of you know, for the last 6 months or so, I've been trying to fix a few health issues that had sort of challenged me for the last 3 or 4 years, vision and mobility, and fortunately I was able to find a good eye surgeon who kind of fixed things up in December. And more recently, I had a hip replaced, and I've just finished getting through the rehabilitation period for that. So one of the things that spending so much time in doctors' offices and hospitals and beds and so on gives you is plenty of time to think. And one of the things that I have thought about, and moving on from me to things more interesting, was the issue of in tube amps. Often one of the things that you have to do is to match the characteristics of a couple of vacuum tubes. For example, in this amp, schematic came out of the RCA tube manual, but it's just intended to be a prop. The output tubes are type 6V6. It's a very good idea if you have similar characteristics in these two tubes. In other words, if they're pretty well matched. Similarly, these 6AU6s should also be matched. And occasionally, depending on how it's used, these multi-section tubes like this dual triode, 12AU7, it's a good idea if you can match the characteristics of those two sections. That is, if the triode on the left is very, very close to the characteristics of the triode on the right. And sometimes matching is more important than individuals. So, for example, you might have a very high gain tube, but if it doesn't match another tube you have, you might go with a lower gain tube that does match better in order to get better performance in your amplifier. So anyway, that's kind of one of the many things I've been thinking about, and I won't be able to do probably as many videos as I used to do, but I do hope to at least get back, and so this is my attempt to do so. So let's move on and look at that. Here are some thoughts that I've been having on matching tubes. There are a couple of ways to match tubes, and traditionally the use of tube testers, and I'll talk a little more about emission, and yes, I know for those of you that are purists, you can't really use emission to match tubes very well for amps, but we'll talk more about that. Or the use of mutual conductance. And so if you have watched some of my videos on mutual conductance tube testers, the B&K series that I did, and also the Hickok 600A and so on, you know that they are often used for mutual conductance. A better way is to use curve tracers. There are some commercial curve tracers out there that can be used for tubes. Some date back to the vacuum tube day, and some are transistor testers that can be modified to use with tubes. Those are pretty expensive. And so I had considered perhaps trying to construct my own curve tracer for vacuum tubes. In considering that, I was trying to get around the extreme expense of many of these curve tracers. Today they're pretty expensive. And even mutual conductance tube testers can run quite a bit, particularly if they're tested and calibrated and so on. So, I initially started out with the idea of doing a DIY curve tracer. Maybe if I could get back in the lab and get to doing some things again, that might be one of my first projects. Well, in conducting that, one of the things that I looked at was, how would I do that? That is, how could I construct a curve tracer at minimal cost? And let me tell you how that at least what my thinking was. One of the things that I thought about was perhaps using a tube tester as the basis for a curve tracer. Now, you could modify a mutual conductance tester to be a curve tracer, But I was starting out with an emission tester for a couple of reasons. One, unlike the mutual conductance testers, these simple emission testers are pretty cheap. You can buy them on eBay for, well, certainly way less than $100. As in some cases, I have a few that I've paid as little as $15 for, and I have a boatload of them. So, and one of the ones that I have several of are these Lafayette tube testers. So I thought, well, maybe there's a way to modify this. But before you can go there, let me tell you why you might want to use a tube tester as the basis. The first is it contains a number of sockets. And there are even amplifiers that use loctal tubes, but certainly a lot that use 7 and 9 pin and octal tubes. So it's kind of nice that you have all these different sockets available. They have a variety of filament voltages available that you can switch in and out. You also have the ability, using switches like this, to configure the pins. So, for example, this one is in the F position, which means filament. The N position means neutral. The P position means plate, and the K position over here means cathode. So you can set up a variety of conditions on any one of these sockets. You also can read the meter to establish a kind of average current. But before you try to convert a tube tester like this into a curve tracer, it might be useful if I went over a little bit of how these emission testers work. Here is the schematic of the Lafayette tester I was just showing you. It happens to be a TE50A, but most emission testers are somewhat similar to this. This is the filament switch, this is the transformer, the meter, the pin switches that allow you to configure the pins, the power switch that allows you to switch for high power or low power, in other words, high line voltage or low, and a leakage special quality switch that allows you to set up a particular test on a tube. This schematic is a little bit busy, so what I've done is redrawn it a little bit to give you some idea of what the basic circuit is. But before I do that, let's take a quick look at a tube, for example, that we might want to test. In this case, for example, a 12AU7, which is right here. You'll notice that the filament volts, it says, is set to E, which is 12 volts on this tester, and then the F position is set to 4 and it stays there. The pin 9 is set to the neutral, and then let me slide this down so you can see a little better the headings up there, the neutral, and then the P position, or the plate position, goes between first on pin 2 with the load set to 35, and then on pin 7 with the load set to 35. And this gives you a quality reading of the emission of a 12AU7. It's a dual section tube, so you do 2 tests. So what's actually happening when you do this? For that purpose, I redrew the schematic. You may notice that here is the transformer, and the reason that I drew it this way is this is not an isolation transformer. In fact, this tube tester does not contain any isolation. Everything inside the circuitry is live. In other words, it's connected directly to, or very nearly directly to, the AC line. When the special switch is in the special position, this is the circuit you actually get. That is, while the auto transformer is across the AC line and you tap off some of that for the filament voltage, the transformer itself is not used in testing the tube. All that is used is a 2.2K resistor, the meter itself, and then the tube. And you may notice a strange connection. The meter is connected to the grid, not to the plate. Why is that? Well, for most tubes, you can actually get more current, or I should say it's easier at a lower voltage to get current to flow from the cathode to the control grid than it is to control to the plate. And so many of these testers, including the Lafayette, actually use pins the control grid pins on this tube. Let me show you on a 12AU7 how that works. But basically, notice what is happening here is simply the tube is being used as a diode. When the AC line is in the correct polarity, current flows from the cathode to the grid through the meter and back to the other side of the AC line through this 2.2K resistor. And what the meter does is simply average the pulses of current. So like any diode, there are pulses of current going through here each half cycle of the AC line. The other half cycle, the tube cuts off. This is a portion of the RCA tube manual for a 12AU7, a medium U twin triode. If we slide over here and look at the pinouts, you may recall that the pins that are used for emission testing are 2 and 7, which are grids. This is grid of triode number 2, and this is the grid of triode number 1. That's what the GT1 and GT2 mean. So basically, the tube is being used with the grid as the plate of a diode, and you are simply measuring the current between those two. So how might you convert a tube tester like this into a curve tracer? My thoughts ran along these lines. Up above is the simplified schematic, and now down here is one of my first thoughts about a curve tracer. Notice that if instead of connecting the grid to this 2.2K resistor, you connect the plate there, and then you provide a bias voltage for the grid, what you are doing now is there are pulses of current flowing through this 2.2K resistor that represent the current through the tube. If you measure the voltage across the plate, and you measure the voltage across this resistor, and you display it in an XY configuration on an oscilloscope, for example, well, you have a rudimentary curve tracer. Now, there's lots of little issues here, but I'm going to point out that when you are matching two tubes, if you can get the operating conditions fairly close to what they are in a real amplifier, you're more interested in how the two tubes differ than you are in the specific circuit you use. So, for example, if you can apply a grid bias that is approximately the same as the bias in the amplifier you're using, and then you sweep the plate with a pulse of current and measure the plate current versus the plate voltage, that gives you an XY representation of this tube's characteristics. Now remember, we're not trying to measure precise transconductance or plate resistance or any of those things. We're just trying to match two tubes. So I set up to do that on the tube tester. However, after experimenting with this for a little while, something dawned on me about the way this circuit was working, and I'll get to that a little later. I'll save that as a little surprise. So let's try this basic method, but instead of having the grid through a bias value, I'm just going to connect it to ground to start with. In other words, I'm going to use zero bias and just see what this might look like on an oscilloscope. So here is what I did with the tube tester. If you remember from this schematic, what I did is I brought a 2.2K resistor out so I could get access to this point. And remember, there's no current flowing through this resistor, so I did that mainly just to provide a little bit of isolation, but with no current flowing through it, the voltage on this side and the voltage on this side are essentially the same. But I now have to get to an issue of safety. You may notice that I have the X connection here, and what that really means is the ground connection of the oscilloscope is connected to the plate of the tube, which is only 2.2K away from the AC line. So why did I mention this? Well, if you know anything about electricity, and you should before you do any of these kinds of experiments, you know that if you're not using an isolation transformer, you'll blow up your oscilloscope, you may blow up yourself. In other words, this can be dangerous if you don't know what you're doing. What I did is I replaced the line cord of the tube tester with a polarized line cord. Then I used an isolation transformer to make sure that none of the connections in this tube tester are connected directly to the AC line. Otherwise, instead of a pretty trace on the screen up here, what you would see is a smoking former oscilloscope. And the reason is that the ground lead of an oscilloscope today is connected to the ground of the power supply, of the power line. And so, as I've said many times before in my other videos, if you're not experienced with electronics, don't try these things. Before you do any experiments on anything plugged into the AC line, you should know a lot about safety. And one way to get that is with a mentor, maybe somebody who has been a ham radio operator for a long time and understands this stuff, or maybe someone that's worked in the industry, maybe a former TV repairman, or somebody like that who can give you some guidelines and can kind of watch over you during your training to make sure you know what you're doing. So here endeth the safety lesson for the day, but please pay attention. You're operating at your own risk when you do these things, and don't do it if you don't know exactly what you're doing and how to follow correct safety procedures. So what do we have on the screen? Well, the yellow trace is the actual voltage coming in from the it's actually the voltage across the plate to cathode. The blue trace is the voltage across the series resistor. In other words, this is essentially the plate current. Notice that when the plate voltage is the right polarity, plate current flows. When the plate voltage is the wrong polarity, no plate current flows. Okay, so now what does that look like on an oscilloscope or on an XY? Well, let's go to an XY trace and see what it looks like. Notice, this is the IV characteristic of this tube. In this case, it's a 6SN7. This part of the trace is cut off, but this is the plate current versus plate voltage characteristic of a 6SN7. So let's take a look at that and see how close that is to what it's shown in the tube manual. Here is the what is called the plate characteristics for the 6SN7. In this case, this is for a GTB, which is what I'm using, a GTB. And you'll notice that this trace is the zero grid voltage trace. Along this axis is the plate voltage, and along this axis is the plate milliamperes. Now, I am using the tube tester in a position where I'm getting about 150 volts across the plate. In other words, the maximum plate to cathode voltage is about 150 volts, which, as you can see, for zero bias is about 20 milliamperes of current. Now, why did I use that particular value? Well, that turns out to be the maximum that you can safely use for the current through a 12SN7. Now, how did I set that up on the tube tester? Here you will notice that I have pin 7 set to the filament position, and the filament voltage is set to D, which is 6 volts. That powers the filament of the 6SN7. Then I have pin 2 connected to the plate, that is the P position. If you recall, that will produce what is in effect this circuit. In other words, the 2.2K resistor is supplying current to the plate, which is pin 3. The cathode is connected to ground, and the grid is also connected to ground, or zero bias. And then the oscilloscope is connected X to here and Y from here to here. And that produces the trace that we saw earlier, the XY characteristics. So, okay, now we have sort of made a rudimentary curve tracer out of an emission tube tester. Where I was going to go from there was compare a few tubes. I have a few 6SN7s, including a couple of Sylvanias and a couple of, I think, Zeniths, each of which are from the same batch. And I was going to compare those and compare the two sides of the tubes, because it's a dual triode, twin triode. So basically you could get, for each tube, you could get 2 different measurements. And with 4 tubes, you get essentially a look at 8 different measurements, and I was going to compare those and so on. Then I was going to match those to what was going on in a mutual conductance tester, which is the way most people balance tubes for tube amps these days that don't have a curve tracer. And then I had an idea. So let me show you where that went. While I was doing these tests using an oscilloscope, for a reason that I still don't understand, I decided, well, I wonder what the meter will read if I were to turn up, now the load control was set to 0, which essentially puts up the 0 ohms across the meter, so the meter is essentially out of the circuit. But I thought, well, I wonder what will happen if I turn that load control up. So let's see what does happen. Well, of course, as you would expect, the meter starts to read. So I turned it up to 100, and I said, I wonder if maybe, since what I'm doing is, with zero bias, I'm flowing a certain amount of AC through this tube, and I'm reading the average value, that is the RMS value of that voltage, which is essentially the current through the tube. What if I just checked 2 sides of the same tube using the meter? As long as I keep the load control in the same position, the conditions will be the same for the 2 parts of the twin triode. So let me do that. First thing I'm going to do is turn the power off. Then I'm going to turn off, down here, pin 2, which is 1 plate, and looking at the 6SN7, I want to turn on the other plate, which, as you notice, is pin 5 right up here. I was using pin 2, plate 2. Now I'm going to use plate 1. So I will turn pin 5 to that position, and I'll turn the power back on, and let's see what happens to the meter. Well, as the tube begins to conduct, the meter starts to move up, and in essence, what I am doing here is I am measuring the conductance of the tube with a 0 grid bias. Well, then it occurred to me that, I can separate the grids by connecting them to the neutral and then using the tube extender. These, by the way, are made by Pomona. They're a little hard to get these days, but you can still find them on eBay. They bring out the voltages of the tube up on top so you can read them with a meter. What if I apply a bias voltage to this tube and then compare for different bias voltages the meter readings for the 6SN7s? Now, what's the advantage of this system over the curve tracer? Because it's doing the same thing the curve tracer is doing. Well, for one thing, I get a very quantitative measure right here on the meter. I can read a number, and there's not as much judgment involved. The downside is I'm just reading the RMS value, but it's no different than a transconductance tube tester is doing. Now, one thing that I will point out is in order to get enough plate voltage to display the characteristics, I had to use the special position of this tester. Special position is designed for those tubes that don't have enough emission at the low voltage that's normally used, which is around 40 volts in this emission tester. But by using the special position, I get about 150 volts peak on the tube, on the plate. And I get enough reading that when the load is set to 100, its most sensitive position, I can read the numbers. So let's look at the numbers for this particular tube. And for that I'm going to zero in. And as you can see, with 60 here and 80 up there, this is almost right on 70. So let me switch to the other position, power off, pin 2, turn off pin 5, power on. Let the tube warm up and see what we get. As you see, it's coming up to about 65, 67, 68, nearly, but not quite, 70. But very close. So what it tells me is I can get a reading off of this tester using this method, but is it any good? Is it just a number, or does it actually give me an idea of how closely balanced these two triodes are? Well, to test that, the best way would be to compare it with a known good tester. In this case, I'm going to use a B&K tube tester that actually tests mutual conductance. Try this same tube. I set up the B&K 707 with 6 volts on the heater, and I got the sensitivity set correctly. Here, by the way, is the tube chart, and over here is the 6SN7. See if it's possible. Let me pull a light up here that might make it a little easier to read. There we go. Okay, 6SN7. You notice 6 volts. It uses socket 25, and it uses a sensitivity of 78, and you use 2 tests, test 1 and test 2. So let's do that. I've already checked for shorts. Now I'm going to do test 1. And you notice the meter reads just about, well, I'm going to call it 84. And now test 2. And you notice it reads just about 85, which is almost exactly what I was getting with the other tester, except I was only getting about 70. So let me adjust the sensitivity until I get about 70 with this one, and then try test 2 and see how much off it is. Well, I'm reading about 71 or maybe 71.5. Let me zero in on the meter just a little bit there. Test 1, test 2. So, except for the setting of the sensitivity control, which of course varies from one tester to the next, it's just basically something that you use and then you calibrate according to that. What I'm getting on this tube is basically the same results, whether I match using a mutual conductance tester, and you notice this is a dynamic mutual conductance tube tester, or whether I use an emission tester set up in the manner that I've been talking about. So from there I thought, well, maybe it might be a good idea to do a few more. So I got out 3 more 6SN7s, The first one came out of this box down here, out of my stash of tubes. 2 are by Sylvania, the one I've been using, and this one. And 2 are from Zenith, this one and this one. They're all 6SN7 GTBs. And so now let me try them on this tester, that is the mutual conductance 707, and on that actually unmodified, but with a little creativity reconfigured to read semi-mutual conductance on an emission tester. Before I show the results, I thought I would show the setup that I used for a bias. In other words, instead of just using 0 volts on the grid, here, for example, I am using the low line voltage setting, and I'll talk more about that in a second, and a power supply bias of 0.8 volts. So, turn this off, maybe you can read a little. No, it doesn't seem to make any difference. The, maybe down here, yeah, that's better. Okay, so I did a series of these, and let me show you kind of the results, but I said I would mention this. What I've also done is I took a set of readings in the high line voltage position. I also took a set of readings in the low line voltage position. The reason is that in the high line voltage position, there's about 150 volts on the plate. In the low line voltage position, remember that it boosts the low line voltage, there's 170 volts on the plate. That's the peak on the plate. So the readings will be a little bit higher. So let me show you what those results were. So here are the results, and let me explain a little what these columns are. This column is the readings I got for the published settings on the B&K 707. I also ran the same test on the B&K 650, which reads out in actual transconductance. In other words, this is in micromhos. Now, I should point out that the 707 and the 650 test these tubes under slightly different conditions. And this is one of the issues that I was talking about early in the video, that tube testers vary from one tube tester to another, and while they're supposed to read out, at least the ones that read out in micromhos, they are supposed to read out in exactly the same transconductance, the fact that they test under different conditions, in other words, different plate voltage or a different grid voltage or a different bias voltage on the grid, and by grid voltage I mean the AC voltage that's used to do transconductance versus the DC grid bias, and also the plate voltage in the case of a triode. Similarly, if in the case of a pentode or any other multi-element tube like that, a tetrode or whatever, you also have to consider the screen grid or the voltage on the screen grid. So, at any rate, here is what I got, and this is for tube A section 1, tube A section 2, tube B section 1, and so on. And as you see, for example, this tube is very well matched. It gets an 84 on one side of the tube and an 85 on the other, and that's really trivial. But this tube down here, the C tube, notice it gets an 80 and an 86. Similarly, the D tube. Now the D tube and the C tube are Zenith. The A and the B are Sylvania. So what's interesting is the matching between the sections on the Sylvania tubes is a lot better. They are different. Obviously this tube is a little higher transconductance than this tube, but the two sides have roughly the same reading on a transconductance tester. Similarly, on the 650, you get pretty much the same results. Notice that the D tube, the Zenith, gets a substantial difference, just as it did on the 707. So then the question is, well, what about some of these things that I'm testing, trying to use an emission tester and reconfigure it to do a pseudo transconductance. And by the way, this is not AC transconductance. This is actually what you might call a DC transconductance test, because what we're doing is we are biasing the grid voltage, in this case to 0 volts, and then we are applying a sweeping plate voltage, and we are reading the RMS value. In other words, we're reading the average slope of the line. If you remember let's see if I can find the tube chart. Yeah, here it is. What we are doing is we're reading the average slope of this line. Okay? So I did that using the TE50 at 150 volts. Then I did that and 0 bias. Then I did the same thing, but with the power switch of the TE50 put in the low position. In other words, so that it applied a higher line voltage, or the equivalent of a higher line voltage. It boosted the line voltage, which is another way of saying it boosted the plate voltage. But once again, 0 grid bias. And I got these figures, and we'll talk about those in a second. And then finally, what I did is, at that boosted value of plate voltage, 170 volts, I also applied 0.8 volts of grid bias and did the same test to see what would happen. Well, obviously, you get lower numbers as you add negative bias to the grid. But what I was really trying to do was to move the grid bias down a little bit and see what the effect was. And 0.8 is probably about in the middle between these two lines. And so you expect less conductance with a more negative grid voltage. But here is what is interesting. Notice that, for example, in this Sylvania tube, where the 707 and the 650 showed that the two sides are relatively balanced, so did this test. So did this test, and so did this test. Down here on this tube, where the 707 and the 650 showed that there was a substantial difference, 80-86, and in the 650, 44-20 and 47-10. And by the way, these last digits are just my estimate. It's 47 and a little bit more is basically what this is. But similarly over here, you see, we did get a substantial difference, 64-67, whereas on this tube, 69-70. So in other words, it's not the absolute numbers that matter, it's the relative numbers. And notice that on this tube, where there was a fairly substantial difference, at 150 volts and 0 bias, we didn't see as big a difference. We went from 70 to 68. When I increased the plate voltage to 170 volts, which is more comparable to the plate voltage that these testers use, then I got a substantial difference, 93 versus 87, or a difference of 6. Similarly, on this tube, 83 versus 86, a difference of 3. Whereas the balanced tubes, the Sylvanias, were still within 1. So, what do I conclude from this? Well, what I conclude is that this method, while maybe not quite as accurate as using a transconductance tester, does allow you to do some tube matching. Now, I wouldn't try to claim that these numbers can be directly translated into micromhos or anything like that. Remember, what we're trying to do here is simply match tubes, and in this case we're matching the two sections of a 6SN7. So, if you looked at these numbers, you would say, this is a pretty well-matched tube. This is a pretty well-matched tube. This one's not quite so good. This one is even worse. So, if you were selecting tubes to use in an amplifier, you would put these tubes, that is the two down here, the zenith tubes, in those parts of the amplifier where balance doesn't matter. Whereas you would put these two tubes, that is the two Sylvanias, in that part where balance does matter. Now, once again, I'm not claiming that all Sylvanias are better than all Zeniths or anything. These just happen to be 4 tubes that I picked out of a set of new old stock tubes that I have. And once again, this may be different for a different tube type, like a 12AU7, and maybe in the future I'll do some other tubes this same way. But for right now, what I am happy to report is that you can, by merely setting the switches on an emission tester in the correct way, and understand different emission testers might not work this way, or this well, or they might work better. But for the TE50, what I found is that if you use the boosted line voltage position, that is the 170 volts on the plate, that you get pretty good correlation between the meter readings with zero grid bias and the matching that you would get if you were to use a mutual conductance tube tester like the 707 or the 650. So I hope this has been a useful exercise. I am going to go on and probably do a few other things, but this video has gotten way too long, so I'm going to break it off here and hope that you got something out of this, and if so, then very good. Maybe we'll do some more along these lines in the future. In the meantime, have a nice day.